Hi everyone, today we are going to start talking about exponential and logarithmic functions, and we're going to focus on graphs and their characteristics first. So in this video you are going to learn how to look at an exponential function and figure out if it's a growth or a decay. You're also going to be able to do that with logarithmic functions. We're going to be able to figure out whether they're growths or decays. Then after we have a graph, we're going to be analyzing the characteristics. So we're looking for discontinuities, domain, range, in behavior, intercepts, all those normal things. We'll do a little bit with transformations of the parent functions to graph exponentials, and then we will also be making good use of the logarithm and natural logarithm buttons on the calculator. So I'll show you how to access those as well. Okay, so first let's talk about exponentials. I thought we might start by getting a graph of these two and then kind of looking at those characteristics. So first, let's look at this example 2 to the x power. So if we wanted to make a table of this so that we could graph our ordered pairs, let's think about what 2 would look like in each of these. Let me remove my keyboard so it doesn't get in the way. Okay, so if we plugged in -3 to this function, that would be 2 to the -3rd. Remember, negative exponents flip that base to the other side of the fraction bar, so that would be 1/8 once we simplify that expression. If we plug in -2 as the x, that would be 1/2 squared when we flip it, or 1/4. When we plug in -1, it would be 1/2 to the first power, or 1/2. When we plug in 0, any base raised to the 0 power is just 1. We can plug in 1, we can plug in 2, and we can plug in 3. Okay, so let's plot these ordered pairs, and I'm actually going to start on the right so I don't have to deal with the fractions first. So 3, 8 is there, 2, 4 is there, 1, 2, 0, 1. Do you see how what started by looking like a pretty straight line is starting to curve a little bit? Look at what happens once we get into those fractions. At -1, it's at 1/2. At -2, it's down at 1/4. And at -3, it's at 1/8. It's getting closer and closer and closer to the x-axis. That's going to indicate to us, because no matter how far we go to the left with our negatives, we're going to keep getting closer and closer and closer. That indicates that we have an asymptote, because we're never going to cross over. These fractions are just going to keep getting smaller and smaller and smaller, like 1/2, 1/4, 1/8, 1/16, and so on. So what's happening here with this graph is that we have this kind of hockey stick shape, right? We have this curve that's getting really close to the asymptote on one side and continuing to go up forever. Because this is an increasing line, that is going to be why we're calling it a growth. It is growing really fast forever. Now, I do want to point out here that you're always going to have exponential growths if the base is a whole number, or an integer, so a number like 2. When we get into decay in a moment, that's going to be a decreasing line, and that decreasing is happening because the base is a fraction. So there's an easy way you could answer a question about is it a growth or a decay, or is it increasing or decreasing, just by looking at the equation. If that base is a whole number versus that base being a fraction. Okay, so let's talk through characteristic sum. We have this horizontal asymptote, that's at y is equal to 0. Remember, we always write asymptotes as equations. And then we're asked one side of the end behavior. As x approaches -infinity, that's the left-hand side of the graph. The function, well, our line is getting really, really close to the asymptote. Remember, it doesn't cross down and go to the other side of the asymptote, it just gets close to it. So that means our function is approaching 0, which is where that asymptote is. Remember, the in behavior, that's the y value, what it's getting close to. The domain for this one is negative infinity to positive infinity because it goes infinitely to the left and infinitely to the right. The range, now this one does have a bottom at the asymptote, so I'm not going to include the 0, that's a soft bracket, but it goes up forever to positive infinity. So now let's look at a decay. Remember this one, because we have that fractional base, we're going to have a decreasing line. So let's plug in each of our x values. So if we put in 1/2 raised to the -3, remember that flips the fraction, so the 1 goes to the denominator and the 2 comes up to the top, so it's 2/1, and then that's raised to the 3rd power, so that's just 8. When I take 1/2 and raise it to the -2, it flips the fraction bar, so it becomes 2/1, and then that negative went away, so it's just the 2 for the square, so that's 4. When I plug in the -1, that's going to give me 2 to the 1st power. Anything raised to the 0 power is going to be 1. When I have 1/2 raised to the 1st power, that's still just 1/2. When I have 1/2 squared, remember that's 1 squared over 2 squared, so that's 1/4. And when I have 1/2 raised to the 3rd power, that's 1 cubed over 2 cubed, which is 1/8. So looking at these ordered pairs, we have 3, 8, -3, 8, -2, 4, -1, 2, 0, 1. At 1, it's only at 1/2, and then it gets even smaller. At 2, it's at 1/4, and at 3, it's at 1/8. So again, we're looking at that asymptote blocking our exponential from going any lower. We have a decreasing line because of that fractional base. That means this is a decay. For this one, our asymptote is at y is equal to 0 again. This time we're asked about the positive infinity side of the x-axis for the end behavior, and this right-hand side on this decay is also getting close to that asymptote, not crossing over it. The domain is still going to be negative infinity to positive infinity, and the range, we still have a bottom at 0 and a top that goes up infinitely. So notice that these two shapes are really quite similar. They both have that hockey stick shape, and they're basically just different in increasing and decreasing beyond much else, and how that changes the direction of our function. So now let's talk about when this basic function gets moved around some or transformed. You are going to be working with a formula that's really quite similar to what we've worked with all year. Notice that our formula still has an h, a k, and an a value. This b stands for base. That was where the 2 or the 1/2 was in the previous problem. So some fun facts: the h is still going to be our horizontal shift. The k value is still going to be our vertical shift. And the a value is still going to be a dilation, meaning it's either going to stretch or compress or be standard. It'll also tell us if there's a reflection if it flips over. Okay, so the good news for this year is that we are going to use a calculator when we're sketching transformations. Next year, you'll be going more into transformations without a calculator. So let's go ahead and look at how we can get some tidbits of information now, but then we also will be using the calculator for this. So because this base of h of x is a 2, that means we're going to be looking at a growth. Remember, we're looking at the base for the exponent that has the x in it. In this one, h is -1. Remember, we always change the sign. K is 3. And the a value is the number multiplied outside of the base. Notice it's not the base itself that's being raised to the x power. So this one, the base is 2. What number can we multiply out here? That's a 1 if we're not changing it at all. So this one has a standard dilation. Okay, so let's go ahead and swap over to Desmos and graph this function. So in Desmos, I'm going to put y is equal to 2, and I'm going to use my Shift 6 to get up into the caret. Now I am going to put parentheses here so that my entire exponent, x plus 1, stays up in the top. If I didn't put that parenthesis, that plus 1 would be moved down to be a base, and that's not what we're looking for. So you need to use those parentheses when you're using Desmos here. Then I'm going to hit the right arrow key to get over back into my bases so that I can put my plus, what was it, 3 there. Okay, so notice there, did you just see how that moved as it went from here to moving up? Remember that k value is a vertical shift, so it moved our function up. The h value moved it, in this case because h is -1, it moved it to the left a little bit. Okay, so let me change this to make it a little bit easier to see all the details that we're looking at. Okay, so we have our graph here. We can see we have a y-intercept that's pretty easy, 0, 5. If you need to graph one of these and get a nice sketch of it, I do want to remind you or show you, if you don't know, when you're looking at exponentials and logarithms too in a minute, Desmos has this really nice feature where if we click on the edit wheel, it takes the equation that we just put in, and do you see this option to convert to table? This is really great because what it's going to do is it's going to take this function and it's going to give us the table that in those last 2 problems we were generating for ourselves, so we don't have to do all of that work. I'm going to hit the table button, and you'll notice it left my equation up here in the y column, and it's given me a bunch of ordered pairs, and they're all over here on my graph as well. Notice that it's picking out some nice ones for me when it's able to. It does have a couple of a decimal here. If I needed other values, say I really needed to know at 5 what it was, I could type the 5 and it would give me the y value. If I continue to go in order with this and hit enter after I type in the next one, it will let me get as far as I want to see the trend. And if I were to zoom out here, then I'd be able to see more of that as well. Okay, so looking at these ordered pairs, I'm going to go back over to my graph and let's get a graph of this. So let's see, it was at -1, 4, I believe, and then 0, 5, and then at 1, it was up at 7. So we had this graph, and I forgot to mention while we were over here looking at Desmos, do you see how it gets really flat here? If we look in this direction, so I'm going to remove some of this to give myself some space. Okay, so actually let's do this. Let's just put in -3, -4, -5, -6, -7, -8, -9. Do you notice with all of these negatives as I went further to the left here that they're all getting really close to 3, right? They're getting closer and closer and closer and closer. Eventually, Desmos would just start saying that it's 3. And the reason that would happen is because it can't round but so much. So if we were to keep going, it would eventually say that it gets to 3 and stop, but that's just because, do you see how many decimals it's having to include in order to get a number? See, there you go. When you look at these ordered pairs, it changes because it's rounding, but if we look at the table, we can see it's not actually 3. That's rounding so that it can deal with the fact that you would have to go more than 3 decimal places out to get it at -12. You would have to go much too far out. So that means an asymptote is happening at 3. So on my graph, I'm going to draw that asymptote, and then I'm going to connect my dots, being sure that I stay above that asymptote. The asymptote is at y is equal to 3 in this one. Notice that that was where my k value was. That vertical shift is telling me where my asymptote is going to be. My domain is still -infinity to +infinity. My range has a bottom at the asymptote of 3 and goes up to +infinity. This one doesn't have an x-intercept because it doesn't cross the x-axis, and we found that y-intercept to be 0, 5 when we were looking on Desmos. Okay, So we have a graph there. A couple of things to point out. The vertical shift, the k value, that will tell you the asymptote. We're not going to worry so much about dilation and horizontal shift right now because that will be something you do next year. But if you're just asked and given the equation for the asymptote, the horizontal asymptote for an exponential, remember that you don't have to do all the work of graphing it. You can just look at the k value and get that value for your asymptote really quickly and easily. Okay, so let's go ahead now and talk briefly about logarithms. Logarithms are the inverse function of an exponential function. So remember, inverses are when all the x's and y's, when those ordered pairs flip. So if we were to find a logarithm, these x and f of x values in this table would flip. Our x values would become 8, 4, 2, 1, and 1/2, and the y values of those ordered pairs would be 3, 2, 1, 0, and so on, respectively. So when we have a logarithm function, let's look at what these graphs look like. It's still going to be that same kind of hockey puck shape, but it's going to be flipped, going in a different direction. So let's do this log base 10 of x, and I'll talk about more about that log base 10 in a few moments, and a lot more in future videos. Okay, so in my graph, I'm going to go ahead and delete all to get rid of that. Let's put in y is equal to. Then for a logarithm, you have a couple of options here. I can type log and it will convert to that logarithm, and then I can just put my parenthesis and type whatever the input is. Another way to do that is by using the keyboard, going to functions and then over to miscellaneous. You'll see here that you have three buttons. There's the log by itself, there's a log with base A, and there's also this natural log, LN button. These are the three buttons we're going to use as we are graphing logarithms. We're only going to be using a calculator to graph logarithms this year. You'll get more into logarithms in your classes next year. So I'm going to click the logarithm button. It doesn't have a base in the problem, so I'm not going to put one here. And then I'm going to put that x there. Now I do want to point out that the logarithm, when it is used, it always gives you these parentheses. These parentheses aren't always going to be typed in the problems, so you need to be very careful about what's in and what's outside of the parentheses. And I'll show you an example of what I mean by that in a minute. For now, let's just go ahead and get this graph. So I've got my logarithm. I can see it on the graph here. To get my points a little bit more easily, I'm going to go ahead and convert it to a table. Notice that you have all of these values undefined initially. If x is -2, that's over here. There's no function over there, right? At -1, there's no function over there. No matter how far down we go, it's not going to come over to this left-hand side of the graph. Notice that 0 is undefined, but look how it looks like it goes right over top of 0. That's because there's an asymptote there. And then we have 1, 0. If I 2, I could keep going down if I wanted to. Oops. And get some more numbers if I wanted to try to find a nice easy one. Eventually at 10 I would get there, 10, 1. So I'm going to graph 1, 0, and 10, 1, I think, on my picture. Maybe, there we go. So 1, 0, and 10, 1 is there. It looks like that asymptote was at the y-axis, so I'm going to put that at x is equal to 0. And then I'm going to graph this with just these 2 points because all the ordered pairs were in between there. So that's roughly my shape. Now, some things that I want you to notice here. Notice that for a logarithm, we now have a flipped asymptote. Instead of having a horizontal asymptote like we had before, we've got a vertical asymptote. The x and the y flipped. The domain and the range are also going to be flips. Did you notice that for the previous problems for the domain, we had all real numbers for all of them? They went infinitely to the left and infinitely to the right. Now that all real numbers is going to be our range, because remember, we flip with inverses. The range goes down forever and up forever. So that's going to be all real numbers this time. Any logarithm is going to have a range of all real numbers the same way that any exponential is going to have a domain of all real numbers. The domain for logarithms is going to depend on that asymptote because the left-hand side in this case gets stopped at 0. So it's stopped at 0, or it starts at 0, and it goes infinitely to the right, to positive infinity. Let's now look at one of the other types of logarithms, a natural log. So let's graph this one in Desmos. I'm going to clear those out. And this time you can either type ln to get the natural log, or again you can use those function buttons and go to the ln or natural log button, and it'll get you to the same place. You type in your function and we get our graph. I can use the wheel to edit the function to convert to a table. Notice that again we have things undefined and it looks like we have a vertical asymptote, and then we start getting some ordered pairs that we'll be able to graph. It doesn't look like we have any nice numbers other than 1, 0, so I'll probably round a little bit between 7 and 8. Let's put that at 2. All right, so we had 1, 0, and then between 7 and 8 it was up at 2, so we'll put that there. We had a asymptote vertically, and there is our logarithm. Notice that it has the same shape as our logarithm that was base 10, our regular logarithm. This is a special type of logarithm that we'll talk more about in a future video. For now, I just want you to be able to find those buttons in the calculator and get our pictures. The vertical asymptote for this one is still at x is equal to 0. The range, remember, is still going to be negative infinity to positive infinity because it goes infinitely down and infinitely up. The domain in this one starts at that asymptote and goes to the right forever. Okay, so I did want to mention one piece about the parentheses that I talked about earlier. If you are given a function like this to graph, that is different than this. Notice in the second one, the x plus 2 is entirely in parentheses. So that means when I'm typing it in the computer, I'm going to put the whole x plus 2 inside of the parentheses. In this first one that I typed, because there are not parentheses, you should assume that this first piece with the x is the part that's in parentheses. We have h and k values. We're not going to get into transformations this year, but this thing being added on the outside, that's a k. The h that's in here with it is 0. So those same principles are going to apply, but it's going to not always have the parentheses typed. So I want you to be really careful and ask me questions if you're not sure about where the parentheses and where the values should go in relation to those parentheses. Okay, so with that, I would like for you to go ahead and try those now you try problems. Now, you should be able to look at an equation and determine if it's a growth or a decay, depending on what that number is. You should be able to identify characteristics after looking at a picture. That means discontinuities, the asymptotes. You should be able to find them and write them as equations. Domain, range, and behavior, and intercepts. You should be able to do some work with transformations, especially with how the vertical shift for an exponential can tell you where the asymptote is, and you should be able to use those buttons on the calculator. Go ahead and give those now you try problems a shot, and then we'll check your work.